This is a particularly important and useful introduction here we're going to make. There are two special triangles, and those special triangles produce three special angles. There are two special triangles, and there are three special angles. Now, I have one triangle here and one that's not a triangle. What I have here is an equilateral triangle, so all the sides are the same length. Let us assume for now that all sides of this triangle are 2. Over here we have a square. All right? Now, for reasons that'll become clear later, all sides of this square I'm going to assume are 1. So all sides of this, now this is not to scale obviously, but all sides of this equilateral triangle are 2. All sides of that square are equal to 1. Now, we know the angles in both of these figures. We know these angles are all 90. And we know these angles are all 60, because if they're equilateral, it must be equiangular. All the angles are the same size. And since there are 3 of them, and the grand total is 180 degrees, that means that each angle must be 60 degrees. Now, in this triangle, I'm going to do something very particular. From this point, I've drawn it in this unusual orientation for a reason. If you draw from this point perpendicular to the other side, that forms a right angle. But what we also know from our studies in basic geometry is that if you drop the perpendicular from this angle, two things happen. Number one, you bisect this angle. Bisect means you cut it into 2 equal parts. You bisect this angle. Since the original angle was 60, that means if we bisect, this angle must be 30 degrees. This angle is 90 because we know we've dropped a perpendicular. Well, this is 30, and we know the grand total must be 180. Then 30 plus 90 plus 60 is equal to 180. So this angle is 60 degrees. Well, we knew that was 60 degrees because that was true in the original triangle. So, number one, this perpendicular bisects this angle. But it also bisects this side. This side has now been cut into 2 equal pieces. If the grand total was 2 at the original, then this in particular, this one must be 1. This hypotenuse is 2, this side is 1. Now what we're going to do is ignore this half of the picture. Consider that special triangle and the angles it produces. So this special triangle produces 2 of our special angles, 30 degrees and 60 degrees. Now, one piece of the puzzle that's not yet filled in, what is the length of this third side? Well, the length of this third side is found using Pythagoras. Let's say we don't know this. So I do know that x squared plus 1 squared is equal to 2 squared because of basic Pythagoras, which means x squared is equal to, let's say x squared plus 1 is equal to 4. So x squared is equal to 3. You don't need to do this computation. I'm just showing you where the number is going to come from. And if x squared is equal to 3, that means x is equal to positive or negative square root of 3. I'm not on a coordinate system. I'm just using distance. And distance cannot be negative. So with that proviso, then we're not going to use the negative distance. X is equal to the square root of 3. So this came from the original triangle, side 2. This was given. This was because we bisected the base. This is 1, and this comes from Pythagoras. So this side is given by the square root of 3. Do not hit a button on a calculator and get 1.7 something something something. Don't write it that way. Write it as the square root of 3. So here's one of the special triangles, and the 2 angles that are special are 30 degrees and 60 degrees. Now, we're going to do something similar here. Not exactly the same, but similar here. What we're going to do with this picture is we're going to draw a diagonal. A diagonal of that square. And consider this angle, badly drawn as it is. Well, we know that the diagonal of the square forces this to become an isosceles triangle. This triangle is isosceles because 1 is equal to 1, which means the base angles must be equal. So these are the same size. Whatever they are, they're the same size. But they're the same size, but they must, because they're acute angles in a right triangle, they must also be complementary. Just like these are complementary. They add up to 90. These must add up to the same amount. These must add up to 90. So that the grand total in the triangle is equal to 180. Well, if they're the same size, that means this is x and this is x. But if you add them together, they must total 90. Well, that's not very hard to figure that x is 45 degrees. So each of these angles is 45 degrees. Just like we ignore the other triangle here, we're going to ignore this top triangle in this picture. And we have another special triangle. This is 30, 60, 90. This is 45, 45, 90. And if any of you have done any work in high school with drafting, for example, these special angles, these special triangles, you actually have a physical triangle. One of them is 30, 60, 90. One of them is 45, 45, 90. And so this is 45 degrees. That is the other special angle. So the special angles are 30 degrees, 45 degrees, and 60 degrees. Those are 3 special angles. They have special properties, special values that are going to be specially worked with as we go through the course. So, 2 special triangles give rise to 3 special angles. 30 degrees, 45 degrees, and 90 degrees. 30 degrees, 45 degrees, and 60 degrees. Sorry.